Hello. Today we're going to be talking about Newton's laws of motion, which we can find in Chapter 3, Section 2. So first law of motion, there are three that Newton kind of came up with and we deal with to this day. We're going to deal with them in order. So here is the first law of motion. Newton's laws of motion relate to change in an object's motion with the forces acting on it. So it's an object that is either moving or non-moving, and then the forces that act on it. So the first law of motion is this: an object moves at a constant velocity unless an unbalanced force acts on it. Remember, for balanced forces and unbalanced forces, we're talking about the net force. And an unbalanced force means there's a unequal force somewhere acting on it. And this is also, by the way, the first law of motion is also called the law of inertia. What is inertia? Inertia is the tendency of an object to resist any change in its motion. And here's a picture of a car moving, and it has a red block on top of it. And the car and the block both share the same velocity. They're traveling together. And what happens is the car hits the block and slows down dramatically, but the red block continues to go at the previous velocity of the car that it was traveling because it still has inertia, which means it does not want any change in its motion. And this is why seatbelts are really important to have in your car, so you don't keep going when your car stops. Inertia and mass. So does a bowling ball have the same inertia as a golf ball? So, and one of the things I like to say is, what would get hurt more if you tossed a bowling ball or you tossed a golf ball? So what is the major difference? The major difference between those two is the mass. The bowling ball is vastly heavier than the golf ball. And remember, mass is the amount of matter in an object, and inertia is fundamentally related to that mass. So the more mass that you have, the greater inertia that you have. So here's kind of a way we can look at it. We have mass and force. This is inertia. So kinetic energy, the object in motion that has mass, then it has inertia. This leads us to the second law of motion. Newton's second law of motion describes how an object's mass, acceleration, and the forces exerted on it are all related. And this is the one of the laws that is easily written down as a formula. So we know that the force and acceleration, if you have more force, then obviously you accelerate greater. It's the same example as the Prius or the top fuel dragster. We know that the Prius has not near as much horsepower or force to cause the acceleration, so it cannot accelerate near as fast as our top fuel dragster could. And mass and acceleration, so if we flip this around and we look at force and acceleration, force, greater acceleration. But if we have mass and acceleration, this relationship here, if the force is the same, so if I'm not pushing any difference, we have a lighter object and a heavy object. Obviously, the lighter shopping cart, if you have a light shopping cart and a full shopping cart, if I push the same amount of strength, the lighter shopping cart will go flying much easier than the heavier object, the heavier shopping cart. So force, mass, and acceleration, they're all related. We know this intuitively in all the things that we played around as kids, cars on the floor, moving and shoving things, all that kind of stuff. We know intuitively about force, mass, acceleration. We just, the physics, we change the words around or give them new definitions, new meanings, so we understand and can actually calculate what's happening. So here is our formula. The second law of motion equation is acceleration in meters per second squared equals net force, which is in newtons, and mass in kilograms. It's also usually written F equals ma. So a force of an object is a product of its mass and acceleration. So we multiply the mass and the acceleration, and we get force. And this is one of the ways to write that one using algebra. So acceleration is force divided by the mass. And we can see with that formula that if we have a greater mass or lighter mass, that dramatically impacts our acceleration. So the second law of motion equation can also be used to calculate net force, which is the F equals ma that we talked about, if we know our acceleration and the mass. So for example, if a helicopter's mass is 4,500 kilograms and the net force on it is 18,000 newtons upwards, what is this acceleration? So we can now, knowing we need the newtons divided by the mass to get acceleration, we can do that math. And here's another one. What's the net force on a dragster with a mass of 900 kilograms if its acceleration is 32 meters per second. Well, we can know we just multiply mass times acceleration, and that is a whole lot of force. And that brings us to the third law of motion. The third law of motion states to every action, there is an equal and opposite reaction. So when one object exerts force on a second object, the second object exerts a force on the first that is equal in strength and opposite in direction. So you think about when you push on something, whatever it is that you're pushing on, there is an equal force that pushes back. And this is where the net forces and all that kind of stuff, and unbalanced forces kind of come into play, whether or not that works. And most of the time, like if I'm pushing on a coffee cup that's sitting on a table, the force pushing back is static friction. It resists the movement, so it pushes back. But if I push with enough force, I overcome the static friction, and that turns into sliding friction, which is still pushing back against my coffee cup that I'm trying to slide across the tabletop. Okay, but remember, one force does not cause the other force. So, like, it's not a I push you and then you push me back. It doesn't happen sequentially. It happens at the same time, and that is how the forces work. The static force is there because I am pushing on it. I don't push on it and then static force happens. It's simultaneous. Okay. Here's a question. A boat is tied to the dock. Does the rope pull on the boat back to the dock, or does the boat pull on the rope toward the boat? In reality, with physics, it actually is to say they both pull equally together. It's kind of one of those great mind trick questions when you stop to think about it, because for every action, there's equal opposite reaction. So as the boat pulls on the rope pulls back on the boat. So third law of motion also continued. We have forces on different objects. They do not cancel. Okay, remember that. They don't cancel each other out. They're plus minuses, and that's where we have net forces. So the action and reaction forces act on different objects. For instance, a student pushes on the box pushes back with the same force. Okay, so force from the box is 30 newtons, right? The force is on the student because the student is pushing on the box, right? There's static friction in the box pushing back against the student. Can't overcome the friction, so there's net force of 0, which means the box doesn't move. But the friction force in the box is less than the applied force. So if I apply 30 newtons of force, sliding friction once we're moving is 10 newtons, all right? And so that is the net force of 20 newtons. So remember that they don't cancel each other out, even though it kind of looks like they do. Just we use mathematics to determine whether or not which direction the forces are working and all that kind of stuff, or if there's any movement at all, if you can't overcome one force with another. So remember, the net force is the sum of the forces on a single object, which is why we have directional components with a plus and a minus values, and that's how we determine the directional components. Right. Forces, remember, are interactions between objects. Okay? So both objects experience a force from that interaction. Again, pushing on a box. If you ever pushed on a real heavy box, sometimes the box actually starts to collapse before you can get the box moving. Or like, say you're picking up a heavy box of cat litter and you have that nice little strap, but if you pull too hard, the strap actually breaks because it's an interaction that both forces are dealing with. The force of you pulling, the force of gravity pulling down, the amount of force that object can sustain and stay intact. And so think of, again, the student pushing on that box and talked about how boxes can crumple. Since the forces are equal, both objects experience the same amount of force regardless of the size of the object, which is why when you punch someone, your hand can hurt. Or you slap for a good high five and all of a sudden your hand hurts as much as the person's hand that you slapped for a really energetic high five. That's reason because there are forces that both objects experience, both of your hands experience. For instance, here is figure skaters. And we have the male figure skater here is kind of pivoting here on his skate. And so he's staying relatively motionless while the female figure skater here is being flung in a circle around him. I don't know if you ever watched that. It's pretty interesting watching a couple figure skating and the different forces that happen and how they catch and stop and their forces all work together. It's really kind of it's pretty cool to watch when you have physics in mind when you're watching things like that. And remember now, they're both experiencing an equal force. Their hands, as they're joined here, that's the pivot center, and so his arm is feeling the same amount of tension as her arm is, so they both have to be gripping with equal amount of strength to offset that. Another example is the bug in the windshield. Both objects experience the same amount of force. Obviously, the bug is much smaller and can't resist the force that's impacted against it, which is why it splatters all over your windshield. And your windshield hardly seems to take any impact at all. But if you were to increase that, say a rock or a pebble, and sometimes when it bounces off the windshield, what happens to your windshield? Right, it cracks or it fractures because of the force that both objects feel when they experience a interaction.